Okay, hello everyone. Welcome to another lecture of deep learning theory and data science. Today we have a special guest, which is Kevin's beautiful cat. I like his face, very nice. So last week we spoke about, I feel like he's staring at me. Last week we spoke about, maybe I should stop looking at him, about logistic regression and multinomial logistic regression. And today we're going to continue discussing those algorithms. And today's lecture is going to discuss a paper that has been quite influential in the deep learning theory community in the last couple of years. And the paper is by Daniel Sudri, Elad Hofer, Morspiegel Naxon, Surya Gunasekar, and Nathan Srebro, who goes usually by Nati Srebro. So the main authors actually come from the university where I did my PhD. And the last author, Nati Srebro, is actually the person who originally taught me machine learning. I took his course in machine learning. So Nati is actually part of the Toyota Technological Institute at Chicago, but he spent 1 year, I think it was somewhere around 1 year at the Technion. And during that 1 year, he gave a beautiful course in machine learning that I attended. I was even supposed to TA that course during my graduate studies, but unfortunately things didn't happen in the end because Nati returned to the US. So I would like to first of all read the abstract of the paper because I think that it describes pretty well what the paper is all about. So the paper is called The Implicit Bias of Gradient Descent on Separable Data. And the paper says the following. We examine gradient descent on unregularized logistic regression problems. So when they say unregularized, oh, maybe I should use this thing. When they say unregularized, they mean that there is no weight decay. So they're not penalizing or penalizing the L2 norm of the weights in any shape or form, with homogeneous linear predictors. So what does it mean, homogeneous linear predictors? This is a fancy way of saying that the logistic regression that they're considering is W transpose X and not W transpose X plus B. There's no bias, so to speak. Okay. So this means homogeneous linear predictors. And then the most important part on linearly separable data sets. What does it mean for a data set to be linearly separable? Does anyone have any guess? I guess it is can be separated by a hyperplane. Exactly. That is exactly correct. I'll elucidate in the following slides more in detail what linearly separable means. But at this point, it just means that you can separate with a hyperplane, right? Cats, dogs. We show the predictor converges. So when they say the predictor, they mean the W, right? We show the predictor converges to the direction of the max margin solution. Max margin solution. What does the word what do the words max margin solution mean? So max margin solution, it's a very special type of a solution. It's a very specific type of a solution, and I'll explain later what is the max margin solution. But intuitively speaking, if you have data which is separable by a hyperplane, right, there could be many type of hyperplanes that can separate the data. So let's do an example. Imagine this is, you know, so this is a data set, right? And here you have other example. Oh, maybe I should use circles instead. More clear, right? So this data is linearly separable by a hyperplane, right? But notice that there is a bunch of possible solutions. Like this is a possible hyperplane or a classifier. This is another possible classifier. There is infinite possible classifiers separating the two classes, the red class and the blue class. The blue is the dog and the red is the cat, right? So when they say the max margin solution, they mean the solution that is maximizing some type of margin. And I'll explain later what does it mean. Justin says the separating hyperplane is as far away from any point as possible. Yes, that is exactly correct. Yes. So the result also generalizes to other monotone decreasing loss functions with an infimum at infinity. So basically the result does not really depend on using the loss in logistic regression. You can do different losses. It generalizes to multi-class problems and to training a weight layer in a deep network in a certain restricted setting. So the result is, in some sense, general. Furthermore, we show this convergence is very slow and only logarithmic in the convergence of the loss itself. Oh, and then there is a very important sentence. This can help explain the benefit of continuing to optimize the logistic or cross-entropy loss even after the training error is 0 and the training loss is extremely small. So here there is a bunch of important words. First of all, what is the difference between logistic regression and the cross-entropy loss? So if you remember in the previous class, we talked about, for example, multinomial logistic regression, right? And in a previous lecture, we mentioned the cross-entropy loss that is being minimized in deep learning. What is the relation between the two? So in fact, the two are equal to each other. So the cross-entropy loss in a deep network is in fact equal to the objective that is being minimized in multinomial logistic regression. So one way to see it is that if you go back to, let's say, the first lecture where we talked about the cross-entropy loss, you would see something like loss is equal to, let's say, sum over the examples from 1 to capital N. And then you would see something like minus log probability of the softmax, and that would be something like, let's write it, minus log probability of the softmax, which is the exponent of WC transpose, let's write it this way, WYI transpose XI over the sum over the exponents of W, let's call it J, sum over J of XI. Does this look familiar at all? Or is this the first time you see something like this? Does this look somewhat familiar? So in this specific, yeah. Oh, by the way, a better way to write this would be the following. You could write this as instead of x, you should write here something like f of xi theta. Oops. Let me write it like this. It's a better way of writing it. F of xi theta. So essentially, if you look at the definition of the cross entropy loss, the cross entropy loss depends on the minus log probabilities of the softmax. So it's essentially equivalent to a multinomial logistic regression model. So that's why you can see how the authors of this paper say either logistic or cross entropy loss. Logistics would appeal to statisticians, cross entropy would appeal to deep learning people, right? When you write a paper, you want to appeal to as many people as possible. So you should use as many descriptions of the same thing as possible. And then the most important part here, they say, even after the training error is 0 and the training loss is extremely small. So what do they mean by that? So there was a phenomenon observed in deep learning where people would train a model and track the error, right? And there's the test and the train error. So this is train, let's say. The train error would at some point just become 0 because your model is so large, it can achieve 0 error. It can memorize all the training examples. It can classify all the training examples correctly, which is why the train error is 0. However, the test error behaved in the following interesting manner. So it decreased, and then it continued decreasing even after this special point, which is called the point of interpolation. So there is a point of interpolation when you've managed to classify your data correctly. And after that, if you train your model even more, your training error does not decrease because it's just 0, but your test error does improve. So, I mean, Reza mentions generalization error. Generalization error is defined to be the difference between the test error and the train error. Okay, it's just a word. And in this, once you hit 0 train error, the generalization error is equal to the test error. If the training error is 0, all the gradients are in fact not 0, not 0. Because there is a difference, there's two different important, there's a distinction to be made. There is the train error and there is the train loss. Train error, train loss, train error, train loss. Train error means that you're, if the train error is 0, it means you're classifying things correctly. But it does not mean that your loss is 0. So you're, okay. Practice makes perfect. So is this paper saying that even when training error is 0, it may not be the max margin separated? Exactly, that is correct. And if you train it more, it converges to the max margin. That's exactly correct. Yes, 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 that is correct. So let me repeat this to the audience on the YouTube. So Xiaoding is saying, so is this, by the way, people on YouTube seem to be subscribing, but not liking. I'm not sure why does no one like? Do you think it's against U of T policy for the grade to depend on likes on YouTube? I feel like this breaches some basic rules at the university, right? It's like 1% of the grade is based on how many likes you made. So is this, oh, so Xiaoding is saying, so is this paper saying that even when the training error is 0, it may not be the max margin separator. And if you train it more, it converges to the max margin separator. That is exactly correct, Xiaoding. So I'm just going over the abstract so you see like a big picture, you know, a big picture. Then we'll drill into the details. So Amireza is asking, sorry, does it depend on the ratio of training set to test set? In this specific case, there's actually no, oh, I see what you're asking. You're asking about the curves, I'm not sure what's the answer actually, Amireza, to your question. In order to answer that question, one would have to conduct experiments across different sample sizes, different training set sizes, and so on. I'm not aware of anyone who did that. I'm not sure what's the answer to your question, Mirza. Okay. So, and then if we continue reading, it says, even if the validation loss increases, our methodology can also aid in understanding the implicit regularization in more complex models and with other optimization methods. So notice this very important word, implicit regularization. What does the word implicit regularization mean, or the words? Does anyone have any guess? What are the words implicit? What's implicit here? What is implicit? Don't explicitly add. Yes, 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 yes. But this can be said in simpler words, Xiaoding. But what you said is correct. So what's implicit here is that you have separable data and you train a logistic regression classifier, right? And so Neo says, is the implicit bias where you pick the hyperplane? Exactly. The choice, the fact that you converge to the max margin hyperplane is representative of an implicit regularization, or people call it implicit bias, because you essentially have an implicit choice. Like if I go on the street of Toronto and I stop a random person and ask them, what does logistic regression converge to when you have separable data? What would that person tell me? They'll say, it just converges to some classifier, leave me alone. But if you tell them it converges to a max margin classifier, they would be shocked, right? Because they would say, like, why would that be the case? And also, if you think about it, the max margin classifier, in machine learning, there's a long history of people loving margins. If you want to make a machine learning person happy, talk about margins. They love margins because there's a lot of theory in machine learning that says that if you have a classifier which has large margin, then you're going to perform well on future data. I don't want to go into that theory because it would take like several lectures at the very least. But on a high level, okay, on a high level, margins have a lot of precedence in machine learning. Okay. By the way, one of the most important things here is, does everyone understand why the last layer, or why the cross entropy loss is equivalent to multinomial logistic regression? Do you feel comfortable with this statement or no? Still confused? Still confused? Comfortable. So, okay, so mixed emotions. One thing you could do, so one thing you could do, I guess, to convince yourself is just go to the PyTorch documentation and look at the definition of the cross entropy loss and compare that to the definition of the negative log likelihood of multinomial logistic regression. And you just see it's the same thing. There is no difference. I think that's the easiest way to convince yourself. So in general, cross entropy is equivalent to negative log likelihood. The difference between a deep network and multinomial logistic regression is that let me do a small comparison. This is deep net, and this is multinomial logistic. So the difference between the two, the loss function in the deep network, which is the cross entropy loss, so cross entropy, is equivalent to the negative log likelihood, okay? in the multinomial logistic regression. In the multinomial logistic regression, you have something called a classifier. Do you remember the classifier? It's basically the W's, the W vectors. In the deep net, the classifier is the last fully connected layer. Let's say last FC, fully connected layer. Do you understand what I mean by last fully connected layer? You have a bunch of layers, and then you have the last layer, right before the softmax. That layer is the last fully connected layer, which is analogous to the classifier. And the last row of this table is the data here. The data in the deep net would be some last layer features. It's the features that go into the last fully connected module. Does this make more sense or no? Yeah. Oh, there was a question. The losses are the same in terms of formula, but the models are different. Yeah, that's a correct statement. The models are different. You could even say that the models are the same in the sense that both of them have a classifier. The main difference is what is it applied on. In the deep network, it's applied on some features that are coming from a bunch of previous layers. Whereas in multinomial logistic regression, it's just applied on the actual data. Okay, so hopefully it clarified a bit. Okay, so this paper that I mentioned here was one paper from a series of papers. They have more than one paper. And another paper they have, it's called Characterizing Implicit Bias in Terms of Optimization Geometry. Now, in part of, okay, so I'm going to show you, probably not today, but next lecture, a very simple, or what I would consider a simple proof for why logistic regression converges to a max margin classifier. And the proof I'll show you is going to be based on this paper, okay? That's why I'm showing you this paper. Okay, so let's try to understand mathematically, what does it mean linearly separable? So imagine you have a data set consisting of examples xi, so this is images of cats or dogs, and labels yi, right, which are one-hot vectors, for example. Then a data set is linearly separable if there exists some classifier w star, so that for every I, it classifies the example correctly. So inner product of w star with xi, where yi is plus, is going to be positive, and inner product of w star with xi, which belongs to the negative class, is going to be negative. Does this make sense? Okay, and equivalently, you could write this very compactly, because we are fans of compactness. You could write it compactly as there exists w star, so that for every I, yi multiplied by w star xi is greater than 0. So does anyone recognize this trick from the previous lecture, right? You remember in the previous lecture, we had yi multiplied by w xi, okay? The magic, yes, the magic. Now, here is again a reminder of logistic regression. So logistic regression assumes that the probability of a label y given an example x is equal to some p for y equal to 1 and 1 minus p for y equal to 0, where the p was 1 over 1 plus exponent minus w inner product x. So this is just, these and these are formulas from the previous lecture, okay? And when fitting a logistic regression model, what we're doing is we're minimizing the negative log likelihood, which is equivalent to the sum of the log of 1 plus x minus yi inner product wxi. this thing. Why? Because you can just go from here to here. So here you have the negative log likelihood, which is the sum of the negative logs, right? Then we plug in, instead of the probability, we plug in this thing, which is the definition of the probability, with this yi trick. And then you just use the fact that minus log, you push the minus into the log and you get log of 1 plus exponent minus yi w xi. Does this make sense? Do you recall such a thing from a previous encounter we had, which took place on Monday? So the negative log likelihood measures the information content instead of the probability. Yeah, there's interpretation of it in terms of information theoretic quantities. I feel like Neo likes information theory. Is that correct, Neo? I feel like you do. There is interpretation. I prefer not to dive into them, but you can definitely find those in different locations. So notice that. Okay, so notice the following thing. In the previous slide, we said that the logistic regression has this negative log likelihood, which is essentially the loss. Now, we are assuming that the data is linearly separable throughout this lecture, right? If the data is linearly separable, it means that these quantities are going to be very large. YIWXI is going to be very large because essentially, imagine something like XXXX, then 0, 0, 0, 0. Then you have a separating hyperplane, and this separating hyperplane is going to cause yi inner product wxi to be always positive, right? Because the data is separable. Now, if the data is separable and all of these quantities are positive, notice that you can always scale w by some alpha, right? And just increase the norm of w, and that way you would decrease this quantity, the exponent, and decrease the loss, the log, and decrease the overall loss. So just by increasing the norm of the classifier, you can push the loss to be very small. Because again, this quantity yiwxi is positive. If you scale it by some alpha, then this thing will become larger and larger and larger. As a result, the exponent will become smaller and smaller and smaller, and the log will become smaller and smaller and smaller, and this whole expression will become smaller and smaller and smaller. So at least intuitively speaking, what ends up happening is that you can replace the logistic regression problem with something that's a bit more pleasant, which is called the exponential loss. The exponential loss says, you know what, in reality, yiwxi is very large, so because log 1 plus z is approximately equal to z, we can just remove this log 1 plus. Just ignore it, and then you get something much easier to work with. So why am I mentioning this? Because if you do the proof for exponential loss, it's pleasant. If you do the proof for logistic regression, it's unpleasant. Now, we like pleasant proofs, right? If you want to say, if you want to explain the relation between the logistic regression and the exponential loss in more mathematically proper words, you can say that both of these losses have tight exponential tails, it's called. Essentially, at the tail, they both behave the same. And so it doesn't really matter which one of them you're analyzing. This is if you want to make this a proper mathematical statement, but for me, it's enough just to say that these losses are similar to each other if your yiwxi are large. Amireza is asking, Xiaoding is asking, so one is big O of another. I'm not sure if I would say that in those words. I'm not sure I would say that. I would, yeah, I'm not sure I would say that. I would say that the two losses are equivalent if you go to a very large YIWXI. So from now on, I'm going to think about the exponential loss instead of the logistic loss. And the main theorem that we'll not prove today, but we'll prove next time, says the following. Assume that you have linearly separable data. So you understand what linearly separable means. It just means you have a hyperplane that separates your data. And assume that you're using an exponential loss. So let's put in parentheses, exponential loss is a cousin of logistic. Basically the same thing, okay? If you really don't like exponential loss, you can make the proof for logistic loss. You will just have to suffer. Not just any higher, what goes through the, yes, it has to go through the origin. That's correct, Tristan. Thank you for the correction. That is correct. And assume that your step size satisfies some strange restriction that will become later clear, where B is the maximal L2 norm of an example. So, it's reasonable to assume that your data is bounded. We're working with images, natural images, can obviously bound them by some number. Then gradient descent will converge to the max margin classifier. So as t goes to infinity, the mean over I of yiwtxi divided by wt2. So what does this whole thing mean? So the t going to infinity just means that gradient descent at a large step or at a large iteration. T is just the iteration, right? What is yiwtxi over wt2? So to explain that, let me show you a picture. So imagine we have here, imagine this is W, the classifier, okay? If this thing is the classifier, then this thing, so there's no way I can do this without being crooked. Oh, good enough. So this blue thing is the separating hyperplane, okay? And you can see the different examples here and here from the different classes, right? Now, imagine I give you an example. This is an example, right? And ask you, please calculate its margin. What would you do? So first of all, you would say, let's assume that W has an L2 norm equal to 1. So just normalize it to have unit L2 norm. And then we just take an inner product between this example, let's call it Xi, and the W, right? And this inner product would give us what? It would give us this distance. Now, what happens if we have a different Xi? So let's say Xj here, which is on the other side of the hyperplane. If you calculate the inner product, what would you get? You would get, does anyone know? What would you get? Negative of the distance, exactly. Thank you, Tristan. And therefore, if you would like to calculate the margin in the negative case, you would do yi w transpose x. I guess if it's negative, it would be like this, right? So yj w transpose xj. So if you're in a positive example, this is equal to w transpose xi. If you're in a negative example, you need to negate the inner product to make it the margin. Amireza says yi equal to +1 or -1. That is correct, Amireza. Yes. Yes. So from now on, whenever we say margin, we can just say that it's equal to this quantity, right? This quantity here. Can we generalize to more classes? Yes, we can. Yes, we can, Gina. That is a wonderful question. But I'll only show it later, not now. Otherwise, it would be too much. So if we go back to the theorem, so we have a question. If the underlying data distribution is truly separable, is maximizing the margin optimal? Asks Justin. I guess optimality depends on when you say optimal, in what sense optimal? In what sense? I guess you mean in terms of performance on test day or something. If the underlying data distribution is separable, I'm not aware of anyone who showed that it is optimal. I'm not aware of such works. I'm not aware. So if we return back to the previous theorem, hopefully now we can understand what it says. So what does this theorem say? So notice that this thing, what is this thing? Does anyone know now? What is this thing? In simple words. The margin, exactly. But this is the margin of the ith example, right? The margin of the ith example. So we can usually denote it by gamma I. And notice that we're minimizing here, minimizing over I. Why are we minimizing over I? Why? Why would we minimize over I? Because you want to find the, yeah, you minimize over all examples. Essentially, you care about what is the example that is closest to your decision boundary, right? So that's the minimum over all the margins, the minimum over all the margins. So minimum over gamma I gives you, for example, this thing, right? This distance. Notice that there's a set of vectors, or a set of examples, I should say, which are the examples that achieve this minimum. And these are usually called support vectors. Support vectors are the examples which are the closest to the margin. So in this case, we have, how many? One. So this is 1, this is 2, 3, 4, 5. We have 5 support vectors. So Justin says something good. He said, since the smallest margin is the one we want to maximize. Exactly. You want to maximize the smallest margin. So what does this thing say? This thing says the margin, as the gradient steps tend to infinity, and specifically it says the minimal margin over all examples, right? The closest distance to the hyperplane. And now we can move to the right-hand side. What does the right-hand side say? It says maximize over W2 less than 1, maximize over all possible classifiers whose norm is bounded by an L2 norm equal to 1. And what you want to maximize is the minimal margin, right? So in simple words, what does this whole thing mean? It means what is the optimal minimal margin you can get. So it's a max-min problem, right? Do you like max-min problems? Have you seen max-min problems in your life? No? Any game theory experts in the crowd? Amireza? Too many. prisoner's dilemma, convex. Okay, so some people do like their max-min problems. Amirezi says only size of support vectors matter, not size of the whole training set. Yes, in some sense that is correct. Yes, in some sense that is correct. Okay, and we will denote by gamma star the optimal possible margin. Okay. Okay, so again, what is the theorem saying? It says that gradient descent on separable data will lead to a max margin classifier. So at this point, let me show you an illustration of the theorem. So the illustration is taken from the paper of Nati and co-authors. So what you can see here is two classes. This is one class, this is the other class. The black line, which is here, is the max margin separating hyperplane. How can you calculate the max margin separating hyperplane? You can solve it using tools off the shelf, but I will not mention those tools. But essentially, people have spent something like 10 or 20 years in machine learning developing tools that give you max margin separating hyperplanes. So just imagine you can do it. And this is the thing you get. And the dashed blue line is the asymptotic solution of gradient descent. So what is this plot trying to tell you? What is this plot trying to tell you? That they are the same, exactly, the same line. They are the same. So gradient descent will converge to the max margin separating hyperplane. I also want to show you another illustration of the theorem, but it doesn't work. I took it from Francis Bach. He has a website and a blog and so on. So I'm going to switch to another presentation, which shows you in an interactive manner. I didn't create this. I shouldn't take the credit. This was created by Francis Bach, or maybe his collaborators. So what do you see here? On the right-hand side, you can see here two classes, right? One class is pluses. Do you see the pluses here? Pluses. You can actually make it bigger. Bigger. Okay, I cannot go any bigger. So this thing is the positive classes, plus, and this thing are the negative classes. This black line is the separating hyperplane. And notice that there is also color. Notice here, notice how there is white color here, right? There is red color and there is blue color. Does anyone have any guess as to what does this color represent? What is this color? Yes, well, exactly. It is W inner product X. Let's try a more cats and chinchillas. Let's try a more challenging question. Does anyone know what does it signify the fact that initially we have white color and shades of blue and shades of red, but at the end of training, we only have dark blue and dark red? Wow, someone actually knows the answer. I'm amazed. Yes, it is because W gets bigger. That is correct. That is correct. So essentially, I think I should mention something. The color, I suspect, is actually not the inner product. It's likely the probability. But the probability and the inner product are cousins of one another, right? So I assume that what they're calculating is, so the probability of class is 1 over 1 plus exponent minus W transpose X, right? Do you remember this? So this is the probability. And the difference, the probability depends on W transpose X. So what everyone was saying was in fact correct. And what I want to emphasize is the following. If you call this thing Z, okay? If you call this thing z, and you try to plot how does this function behave, then what you would get is at infinity, it's equal to 1, and at minus infinity, it's, let me see. So it's supposed to be something like this, right? It starts at 0 and ends up at 1. And this is z here. Does this make sense? So essentially, you can think of the probability as being a function of W transpose X, right? Now, what would happen with this plot? This is a, oops, what have I done? This is the probability here. What would happen with this plot if you place here a scalar inside, something like alpha, and you increase alpha gradually? What would happen is that this plot would become more and more closer to a step function. Does this make sense? Does anyone even, do people know what's a step function? Maybe I should. I'll get to the figure on the left, but yeah, it is correct what you said. I'm Reza, yes. So essentially, what I'm trying to say in simple words is that the probability is a function of W transpose X, right? And W transpose X, you can place there a scalar alpha, which corresponds to, let's say, the norm of W. And as you increase the scale, this function becomes closer and closer to a step function. I believe that is why students earlier said that the reason why, do you see how at the end of training, it becomes very close to either blue or red, right? Either blue or red. It's because there is essentially a step function. This is close to a step function, right? Whereas in earlier iterations, this is not a step function. Does this make sense? Yeah. Not step function, getting closer, step function, right? And on the left, what you can see is simply the classifier as it's traveling. Now, what can you see that is interesting about the classifier? Can you say anything about the classifier's trajectory that pops to the eye? Is that even an expression, pops to the eye? I feel like that's incorrect English. It twists and turns. Yes. But anything a bit more start straight, maybe, but something more. Yes. So the correct answer is that, exactly, yes, Etienne. Hopefully I'm saying that correctly. It goes away from 0. So essentially the norm will always increase and increase and increase and increase. You can actually prove mathematically that the classifier's norm will diverge to infinity. The classifier will keep growing in norm, and that is why this function or this function tends to a step function. Okay, so it seems like we are out of time. Let me just verify what is the next. Okay, so this is a good time to end the lecture, because from now on it's the derivation, and I don't think we can do it in a minute. So thank you for joining, and I'll stay for questions. If anyone is still confused about the relation between cross entropy loss and multinomial logistic regression, that's something I would recommend you to make sure that you either understand or bug me until you understand. That's another option for understanding. Where can you read more about cross entropy loss? I think maybe you could, maybe you should try the deep learning book. Do you know the deep learning book by Goodfellow? Maybe they provide a proper explanation, or PyTorch documentation. I like the PyTorch documentation for mathematical formalisms, which I guess doesn't sound very mathematically formal, but I don't know. Does this max margin bias also occur when you do SGD and pass the training set through batches? What a beautiful question. I think one of the follow-up works by Nati and collaborators looked at SGD, but I'm not 100% sure. I think that some of their experiments were on SGD. So I think the answer to the question is yes, Stephen. But not 100% sure yes. Does the margin depend on the choice of inner product? I'll always I think it does, yes. I think they have a follow-up paper where they study. In this paper, they study what happens if you do an optimization algorithm called mirror descent. And mirror descent is essentially defining a different inner product, like non-L2 norm, and optimizes under that.